Now let's turn our attention to the next part of coordination chemistry. Now that we've named the compounds, we need to take and learn how to draw isomers of the compounds. With this lecture and the next lecture, we will learn about different types of isomers of coordination compounds. You were exposed to this idea in organic chemistry, and this is just an extension of that. Historically, we've looked at Werner's ideas versus Jorgensen's ideas. Remember that Werner suggested that coordination compounds with 6 ligands had octahedral geometry. This led him to believe that there were 2 isomers of this compound, the amine chlorocobalt compounds. There should be 2 different types of isomers of that compound. Chain theory, which was proposed by Jorgensen, suggested that there was only 1 isomer of the 2 compounds. Werner's ideas led to isomerism in coordination compounds. Isomers are compounds with the same types and same numbers of atoms, but with different arrangements of the atoms. So, if we're looking at the compound mentioned on the previous slide with a generic formula CO NH4 or NH3,4 Cl3, you could have this isomer or this one. This isomer has 2 chloroligands cis to one, or 90 degrees from one another, and its color is purple. This compound has the 2 chloroligands 180 degrees from one another. This compound appears green. Eventually, both isomers were discovered by Werner, and this supported his idea known as coordination theory. There are many types of isomers in coordination chemistry, and we're going to learn about each type. We have solvent, ionization, and coordination isomers. This is one group. All of these compounds have the same chemical formula, but different arrangements of the ligands around the metal cation. We will look at examples of these shortly. Linkage or ambidentate isomers. Bonding occurs in these isomers between different atoms within the same ligand. So remember, SCN is a special ligand. It can form a coordinate covalent bond with either the sulfur or the nitrogen. Stereoisomers are they're different. They have different geometric arrangements of the ligands around the metal atom or cation. This is the most difficult group of ions to see, and you've dealt with stereoisomers in organic chemistry before. So we need to start off with a central question. We have 2 molecules with identical chemical formulas. The question is, are the bonds between the atoms in the 2 molecules the same? If we are able to say yes, those are stereo or configurational isomers, stereoisomers. If the bonds between the atoms are different, we have structural or constitutional isomers. We will first look at compounds where the bonds between the atoms are not the same. We will look at the structural or constitutional isomers, and remember there are 4 different types: solvent, linkage, coordination, and ionization isomers. Solvent isomers. They include hydrate isomers. Solvent isomers are isomers that have a solvent, like water, participate as a ligand or is included in part of the crystal structure. We have three compounds with the same formula: CrH2O6Cl3. In the first case, all 6 waters satisfy the secondary valence of chromium, and the 3 Cl minuses satisfy the primary valence. This compound appears purple when you see it. In the second case, you have 5 waters bonded to the chromium and 1 chloroligand. The formula for this compound is CrH2O5Cl, that's the complex ion, Cl2.H2O. So there's 1 molecule of water outside, 2 Cl minuses that form ionic bonds with this complex ion, 5 waters on the inside, and 1 chloride on the inside, satisfying the secondary valence. This compound appears light blue when you look at it. The third isomer is CrH2O4Cl2, that's the complex ion, Cl.2H2O. There's 2 chloroligands bonded to Cr, 4 aqua ligands bonded to Cr, and then the other chloride satisfies the primary valence, and the 2 waters are outside as well. Ionization isomers. This group of isomers have the same chemical formula but give different ions in solution. 2 examples for you to consider are CONH3,5NO3 as the complex ion and SO4 as being outside or satisfying the primary valence. If you look at the structure, you will see that the cobalt is bonded to 5 NH3s, the neutral ligands, 1 NO3 minus, which is an anionic ligand, giving this entire ion a +2 charge. The counter ion is SO4 2 minus. In this example, SO4 now becomes part of the coordination to cobalt, whereas NO3 is outside of the coordination sphere. The compounds have different properties because they have different ligands bonding to the cobalt. Coordination isomers. These typically include 2 or more metal cations. The molar ratio of ligands and metal cations remain the same. So notice that there's 1 PT, 2 NH3s, and 2 Cls. In this case, there's 2 PT, 4 NH3, and 4 Cls. However, the ratio is the same. 1 to 2 to 2. 1 to 2 to 2. But the difference is the way the bonds are, the way the ligands are bonded to the transition metal cations. In the first example, you see that the 2 Cls are bonded to PT and the 2 NH3s are bonded to PT. In the second example, you see 4 NH3s bonded to 1 PT and 4 Cls bonded to the other PT.